Hey everyone, this recording is just going to be a little bit of an extension from the previous recording. Remember, the key concepts that we covered in the previous recording was as follows. First of all, what is centripetal motion? It's motion in a circle. Okay, what causes centripetal motion? A centripetal force, okay, that always acts towards a central point. Now, does a centripetal force act on its own? No, okay, I stressed that to you guys in the previous lesson. Centripetal forces don't exist on their own. There's always an actual force that supplies a centripetal force. An actual force could include gravity, friction, tension from a string, etc., etc. Okay, if we understand those fundamentals, the maths related to circular motion shouldn't be too hard at all. Let's have a crack at just a very standard question that you could get for centripetal motion. Let's just say we've got a car going around a roundabout at, say, 50 meters per second, and the radius of this car's motion is 5 meters. And the mass of the car, let's just say, is 1 kilogram. My question to you guys would be, what is the magnitude of the centripetal force that we would require in order for our car to continue in its circular motion? So we're going to invoke the centripetal motion formula, Fc equals mv squared on r. That should be F subscript c, okay, signifying that I'm referring to centripetal force. Okay, Fc equals mv squared on r, which equals 1 times 50 squared all over 5, okay, which is going to be 2500 all over 5, which is going to equal 500 newtons. Boom, just like that. So we just have calculated the magnitude of the centripetal force required for our car to go around the roundabout, and this force, remember, is going to be supplied by friction, okay, between the road and the tires of the car. Awesome. Nice and easy application there. The question that you guys might ask is, where does this formula come from? Now, to be honest with you guys, you don't actually need to know how to derive this formula, okay? If it's a formula from your data sheet, typically you won't need to know how to derive them, except though there are a few exceptions, so we will touch upon those exceptions in future recordings. But for those who are interested, this is how we derive the centripetal force formula. We know Newton's first law tells us F equals ma, right? So centripetal force is going to equal ma. And using a little bit of calculus, for you extension 1 and 2 mathematics gunners watching this lecture, you can use calculus to find, or to find that acceleration can be written as v squared on r, using a little bit of calculus. I'm going to leave that as an exercise for the extension 1 and 2 gunners. But this is also a result that is on your data sheet, okay, so you don't need to know that. So if a equals v squared on r, we can just substitute that in. Okay, a equals v squared on r for anything traveling in a circle. And this is what, this is how we get our centripetal force formula. All right, perfect. Hey everyone, here's another nice exam style question from the CSSA paper, which illustrates a more difficult application of circular motion. Let's have a look at this. A car rounds a bend on a road that follows the arc of a circle with radius 25.6 meters. The car has a mass of that, and the force of friction is this. Okay, so immediately we know that's our centripetal force. It could also be a good idea to draw a diagram, okay? So we've got circular motion here, radius of 25.6. And yep, at what maximum speed should the car be moving so as to stay on the road while taking the bend? So this is just a simple application of centripetal force equals mv squared on r. Okay, so the maximum centripetal force that we can get from the road onto the tire via kinetic friction is 9,420 newtons, which equals 885 times b squared, which we're trying to solve for, all over 25.6. Now let's just double check we've got our SI units. Radius is SI units, force is SI units, and so is mass. So we don't need to worry about any conversions there. So therefore, v squared equals 9420 times 25.6 all over 885, and therefore v equals the square root of 9420 times 25.6 all over 885, which is going to give you a final answer of, just plugging it into the calculator, 16.5 meters per second. Perfect. And then part B asks us to consider, using physics principles and your answer to part A, quantitatively explain why motorists are advised to drive at lower speeds during wet weather. Okay, this can be answered in one of two ways, but fundamentally they are conceptually similar. Okay, what we need to know is when a motorist is riding in wet conditions, kinetic friction is going to be lower. So you have to make that point. Kinetic friction will be lower, okay, in wet conditions. So therefore, instead of the centripetal force being 9,420 as it was before, your centripetal force and your kinetic friction force is going to be less than 9,420. Now we can use our centripetal force formula to then prove, okay, that if this is lower and your velocity stays the same, your radius is going to increase. If your radius increases, what that means is this car is going to veer off the bend, and it's going to end up, say, crashing into a tree, okay? So that's why for the radius to be maintained at 25.6, your velocity has to be reduced. So another way you can explain that is keeping r constant, velocity has to be reduced, okay, to keep r constant at 25.6. And that's why a motorist is advised to drive at slower speeds during wet weather so as to maintain a constant radius according to the centripetal force formula. Very cool application of centripetal motion there, folks. Hope you enjoyed.